Hello, everyone. Today, we're going to jump right into the rate of chemical reactions. We're going to figure out how to measure and really understand the speed of chemistry as it happens. So let's kick things off with a simple question. How fast is a chemical reaction, really? I mean, can we just say it's fast or slow? Nah, we need to be a bit more scientific than that. Let's see how we can get precise. Okay, so here's what we've got on the agenda. We'll look at what a reaction rate actually is. Then we'll figure out how to measure it, how to put it on a graph, and the big one, why the speed changes over time. All right, first up, what is a reaction rate? Let's start with something you can see for yourself. Picture this. You drop a strip of magnesium into some acid. Right away, you see all these bubbles of hydrogen gas fizzing up like crazy. But watch closely. It starts off super fast, then it begins to slow down, and finally, it just stops. Kind of weird, right? So why does it do that? Well, that changing speed has a name. Scientists call it the rate of reaction. And it's pretty simple, really. It's just a way of measuring how much stuff, the product, is made in a certain amount of time. Or you could look at it the other way. How much of the starting stuff, the reactant, gets used up. Okay, so watching bubbles is cool, but how do we actually measure this in an experiment? Let's talk about how to get some real numbers from what we're seeing. Think about it. If our reaction is making a gas, like those hydrogen bubbles we just saw, we need a way to catch it and measure it. How on earth are we supposed to do that accurately? Turns out there are two really clever ways to do it. First, you can use something called a gas syringe. You just attach it to your flask, and as the gas is made, it pushes the plunger out. Super simple. You just read the volume. The other way is to collect the gas over water. You bubble it into a measuring cylinder that's filled with water and turned upside down. The gas pushes the water out, and again, you can just read the volume. Both methods work great. Awesome. So we've done our experiment, we've collected our measurements, and now we have a bunch of numbers. What do we do with them? How can we see the pattern? Well, usually you'd start by putting your results in a table, right? You've got your time and you've got the amount of gas produced. This is good, but honestly, a table of numbers is kind of hard to understand at a glance. And that's why graphs are absolutely fantastic. When you plot those numbers, time on the bottom, volume up the side, suddenly you can see the story of the reaction. You get this really classic curve shape. Now, you really want to pay attention to the shape of this line. That curve isn't random. It tells us everything about how fast the reaction is going at any point in time. Let's break it down. Look at the very start. The line is super steep. That's where the reaction is fastest. Then, notice how the line starts to get less and less steep? That's the reaction slowing down. And finally, it goes totally flat. That means the reaction is over. It's stopped. So here's the number one rule you need to remember. The steeper the line, the faster the reaction. That steepness, or the gradient, as it's sometimes called, is literally a picture of the reaction's speed. Okay, so we know the speed changes, but why? Why does it start fast and then slow down? To answer that, we need to zoom in, like way in, and think about what the individual particles are doing. It all comes down to something called collision theory, and the idea is actually really simple. For a reaction to happen, the reactant particles have to bump into each other. They have to collide. And not just any little tap, they have to collide with enough energy. And this picture shows it perfectly. On the left, at the start of the reaction, the flask is packed full of reactant particles. They're all bouncing around, so collisions are happening all the time. But look at the picture on the right after a while. A lot of those particles have already reacted. There are just fewer of them around, which means, you guessed it, fewer collisions. So let's just walk through that one more time. At the beginning, you have loads of particles, so you get lots of collisions, and the reaction is fast. As those particles get used up, there are fewer of them left to bump into each other, so the collisions become less frequent, and the reaction slows down. And at the end, when one of the reactants is all gone, there's nothing left to collide with. The reaction stops. Simple as that. Yeah, this really says it all. As the particles react, there are just fewer of them left. Another way to say that is that their concentration goes down. And that's exactly why the reaction rate is highest at the start, when the concentration is highest, and why it drops to 0 at the end. So, knowing why the rate changes is super important. Because if you know why, you can start to think about how you could control it. And that leads to a really cool question.